Okay, so we're going to be moving into new territory here. We're going to kind of take our conversations about correlation and linear relationships to the next level and start to talk about how we use these tools to do prediction. Prediction is one of the core tools in statistics. One of the core reasons we do statistics is to predict outcomes, both in terms of what might happen in the future and in terms of what would have happened under different sets of circumstances, or what would have happened under counterfactual scenarios, right? Those things we did not observe. So prediction is a key tool we use to take the data we did observe and to make guesses about things we did not observe or could not have observed or have not yet observed, right? So prediction is kind of the big game that we're after in statistics. It's the big goal of the entire enterprise. So why should we predict? A, to learn about what's likely to happen in the future. All kinds of reasons we might be interested in that, right? Like weather forecasting models are probabilistic, right? They rely on information about what's happened in the past, models about how weather systems work, and then they kind of project a range of possible outcomes, 40% chance of rain, right? We might also be interested in forecasting elections or economic changes, or we might be interested in prediction to validate theories or arguments, right? So valid causal inference requires successful prediction of counterfactual claims. That is, if we want to test scientific theories, prediction is an incredibly useful tool for doing so using observed data, right? We can make inferences from things we observe to guess what might have happened under alternative circumstances. And if those predictions come true in future observations, that's strong evidence in support of a scientific theory, right? So prediction is also kind of the core of the scientific enterprise, not just the statistical enterprise. Being able to predict what would happen is the hallmark of a strong theory, right? A strong theory can tell us what will happen under particular configurations. If X were different, what value of Y would we observe is kind of the core question in this causal inference framework. So let's start with two data sets. These are going to be the ones we worked with last time as well. And the RMD file for today has been pushed up. So if you want to go to the website, you can download that code to follow along. But again, we're going to start with the polls data and the results data. And last time we focused on how to join data frames together, how to manipulate and join them. So we worked with these last time. We're going to take the results of all that exercise to join multiple data frames together to engage in an assessment of prediction. So how do we join these data frames? We harmonize the data. That is, we give them consistent column names, variable labels, and units of analysis. And here's how I do that with polls. I'm not going to go into too much detail on this because we covered it last time, but well, what the heck, I'll walk through it. Right, so we'll walk through the code on this real quick. This is a lot of code, obviously, but this is how we're going to transform the polls data and the results data to have common shapes and common structures, right? That's called harmonizing them. We want to be able for them to talk to each other. And to do so, we have to transform the data a bit, right? Let's go back here. I'll read in my data. And then we'll look at this polls, this chunk of code on line 49. What we're going to do is we're going to take, first, let's look at what's inside polls. Inside polls, we have individual polls from various organizations that conducted polls in the 2016 presidential election. Each poll has a unique identifier. It tells us the proportion of respondents or the percent of respondents who favored Clinton or Trump. We're restricting this to the likely voters subset, right? If we look at what's inside of polls, we could see that we have all other populations in here. We also have registered voters and adults. So we want to only look at the likely voters to make sure it's close to the actual result. We're going to take first on polls, we're going to filter out everything that's not likely voters on population. Oops, I need to load dplyr in. So let's load in my tidyverse package. Okay. So first, we're going to filter out everything that's not likely voters, right? We're going to keep only likely voters in the data. We're going to select 4 columns. If we go back here, we can see those. We're going to select only the columns we need, right, to obtain the actual insight about what the polls tell us. That is, we need the state, Clinton, and Trump. Really, we only need 3 columns. I'm going to keep electoral votes in here because we're going to use it later. We're going to use that later to help us make projections of the accuracy of the polls. And that's a good place to get that data from. So we'll keep that column as well. We'll keep state, electoral votes, Clinton, and Trump. I'm going to use the pivot longer function to transform it. So let's look at what this looks like just after I run those initial, the filter and the select, right? We get the entire data, but we've removed a lot of columns. Right now we have state, electoral votes, Clinton and Trump. But I want the format to match what we see in results. So let's look at results. In results, I have a candidate, and then I have a candidate votes column and a total votes column. So what I want is I want to transform my polls data from a wide format into a long format. And the difference here is that we actually have a variable in a column name right now. We have Clinton and Trump as column names. But what that's actually, that's actually a variable. The variable is which candidate are we talking about in this row of data, right? Which candidate are we referring to in this row of data? That's a variable itself. And the philosophy of tidy data suggests that all variables should be in columns, not in names of columns. So instead, we can create a new column called candidate that can take on values of either Clinton or Trump, and a new column called %vote that takes on these values. Right? We'll compress the number of columns in the data. We'll put information into the column itself rather than in the name of the column. Pivot wider function allows us to do that. We're going to tell it the columns we're going to use are Clinton through Trump. And in this case, they're next to each other. So it's just going to take those 2 columns. Remember, colon tells us go from here to here. So if we put, for example, on the console 1 to 4, we would get 1, 2, 3, 4, 1 to 99. Right? We would get all integers between 1 and 99. So if I say Clinton through Trump, it'll give me all columns between Clinton and Trump. I'm going to put the names of those columns in a new variable called candidate, names to candidate. I'm going to put the numeric values to, that is the things that are in these columns right now, 38, 41. We'll go into a new column called poll results. So let's see what happens when I run this block of code. Look at the head of this new data frame. And we can see that we have state, electoral votes. Those 2 are unchanged, right? But they now they're kind of duplicated because we've created twice as many rows in this new data frame because we pivoted candidate into its own column. And we've changed 2 columns into 1 with poll result from the numeric values from Clinton and Trump. So, for example, if we look at the number of rows in our new polls data frame, we'll have 1,454 versus in the original set, after we run the filter, let's see what we have. We should have exactly half, 727. We doubled the number of rows by compressing the number of columns. That's why we call it long rather than wide. Wide has more columns, long has more rows. When we're working in R, we typically want to have long data rather than wide data. Some other software packages like Stata or SAS or SPSS much prefer wide data, but it gets really messy really quickly. You'll see why when we get really good at ggplot, that working in long data makes producing informative graphics dramatically easier because we don't have to go to column names to get data, right? We can get the column name, for example, let's say we want to make color attached to candidate. Well, we have that in a variable that we can very easily pass to ggplot as an aesthetic, right? So there's a really good reason we want our data in long format that may be a little opaque to you right now, but as we keep going, I think you'll see the value of it. Okay, so we have polls in this format. Oh, right. It gave me an error because it's already done the transformations, but let's run it again. There we go. Okay, so polls now looks like this, and we want to harmonize results so that we can bring the 2 together. ultimately what we want to do is we want to join the information from results onto the information in polls. That is, we want to know, how did the state actually vote on election day? I have my prediction that Texas would go 38% for Clinton and 38%, or 40, I'm sorry, would go 38% for Clinton and 41% for Trump. What actually happened on election day, right? So I can check how good that prediction was. So again, let's look at results really quickly. The dirty secret of statistics is that data cleaning is like 80% of the work, right? Modeling is 20%, doing the other math. Data cleaning and data manipulation is the vast majority of the time you spend doing statistical analysis. So like learning and getting good at transforming your data into the shape you need it to do the analysis you want is by far most of the work, right? Knowing what models to use, knowing how to interpret models, that's incredibly important. But in a typical statistics course, we spend all our time on that and none of our time on the data work. And I think that's backwards, right? Because it turns out, yeah, at least in my experience, the vast majority of my time spent doing data analysis is doing cleaning and transformation. Okay, so that's why I'm kind of drilling it so hard. Let's look at results. We want to have results from the 2016 election. We can see here that we have results going back as far as 1976. We don't need those, right? All we need is the 2016 election. So first we'll filter. I want to make sure that we don't have like a random governor's election in there. So I want to filter by office, and I can see that US president is a value. So I'll go ahead and filter office equals US president. That's the only election I'm concerned with. I can also see that we have third parties in here. We have the American Independent Party, the Prohibition Party, the Communist Party, the Libertarian Party, right? I don't really want those results for the 2016 election to the extent that there are third parties in there. They weren't competitive and we didn't poll for them, right? So I don't have predictions for them. So I'm going to filter that we only get Democrat and Republican Party. So those are my three filter conditions. Let's see what I get after I run that. Well, lots of data, but we can see then that I get 2016 Alabama, office US president, and I have the vote totals for Trump and Clinton. They're in another column down, but I'll have, they're kind of off the screen right now, but they're in there. And also I see here that I've got a column for candidate like I want, right? But the names won't match. Right now, in the other data, I have Trump and Clinton as the as the strings, that is the group of characters identifying each candidate, right? Trump and Clinton as one word. But here I have Trump, Donald J, and Clinton, Hillary, and those will not exactly match if I try and join them. So I need to modify that. I'm going to use a case when to change Clinton, comma, Hillary into Clinton, and Trump, comma, Donald J into Trump. And then I'm going to select only those columns that I need. I only need state PO, which is the two-letter state abbreviation. I need candidate, and then I need candidate votes and total votes. And I need those two columns to compute a percentage that will match what I have in the other data set, right? So let's take a look at what that looks like. So now we should have a 100 row data set. Maybe if DC's in there, it'll be more. Yeah, 102 row data set where I have the total number of votes that each candidate got, and in a second column, the total votes that were cast. From that, I can compute a percentage very easily, right? I also want to rename state PO into state. The first argument in state, so state equals state PO, tells me that take what was state PO and rename it to be state. So the first one is the name I want to be, the resulting name I want. The second one is the name I'm replacing in rename. I've gotten that mixed up in my head sometimes because it seems like it should be arbitrary. But anyway, once I've run both of these, let's look and see if they're harmonized. Right, we can see that we have state in both is a two-letter abbreviation. Candidate in both is a simple last name. And then we have two variables here, candidate votes and total votes, that we don't have here. and we have one variable here that we don't have here. But what we want is we want to bring these two variables and attach them onto the side of this data frame. We want to add two columns onto this data frame based on the match of state and candidate. That's a join. So to do that, we're going to use a left join. That is, we're going to take the object on the left, and the direction is arbitrary, but polls is going to be the object I want to preserve the structure of, right? I want to keep the structure of the polls data where I have every single poll and every single result. I only have 51 results of the election, but I have like 1,400 polls, right? So I want to keep those 1,400 polls, and I want to attach to them the actual results of the election so I can assess how accurate the poll was. So I'm going to take polls on my left-hand side, and I'm going to join results onto it. So we can think of, when I say left join, it means take the first object I give you, the one that's on the left of the argument, and add in the other object on the right. There's other kinds of joins, but I almost exclusively use left joins in my own work. You can kind of tinker with them to configure them how you like, but I think just teaching one for now is best. There are right, full, anti joins as well, but we're not going to mess with those. Okay, then I'm going to create a new variable called %vote that's simply equal to the ratio of candidate votes to total votes times 100, right? We're going to compute the proportion, the vote share for each candidate, multiply it by 100 to get it in % format. So now we have this new object called polls results. It looks like this. We have the state. So each row is a poll, right? This is poll level. So we have a state that the poll was conducted in. This electoral votes is just a simple indicator that we're going to use later. We have the candidate. We have the result of the poll, of this individual poll. So this block of 2 rows is a single poll. We have the total number of votes that candidate got, and then we have it expressed in percentage format. So if we were just, looking at this, would we say that this poll was accurate or not? And by how much was it off? That's going to be a question that we kind of tackle throughout the day. How do you think we might compute the error for this poll? How could we compute the error for the poll for the Clinton poll results on row 1? So the result of the poll was what? Let's not use hat. Sorry. I use the hat notation to indicate predicted in statistics, but I'll just call it Y sub predicted equals 38. And Y observed equals what? 43. I'm sorry, 43.2. Okay. So we can compute error equals Y pred minus Y odds. Right. So in this case, we could compute the error as 38 minus 43.2 equals negative 5 points. Okay, so we'll call it -5, and we'll be done with it there. So we have an error. This poll actually predicted too low for Clinton, right? Reflecting that we had a lot of undecided voters who didn't express an opinion. This does not sum to 100, right? So there's some voters in here that either said they were going for a third-party candidate or they were undecided. But ultimately, the poll said Clinton was going to get 38, and on election day, she got 43.2. Poll was off by 5.2 points. Okay. So that is crudely the simplest way to compute a prediction error. We make a prediction, we compare it against the observed data. We often don't have both of those things, but in this case we do. So we'll kind of work through the example here. So error is a general term for how wrong our guess is. Right? Error is a term in statistics we use to denote how wrong a guess is from some true value, right? How far away something is from the truth. We can generally calculate error by subtracting the observation from our prediction, right? Prediction error is equal to the predicted value minus the observed value. In this case, the predicted value was the poll, the observed value was the election result. And we can compute this directly as a mutate. I got, of course, booted up the screen, but let's look at what that looks like here. So you can see that we have our errors computed as an additional column here now. Minus 5.24, minus 11.2, plus 1.55, minus 3.22. So we've now computed that as an additional column of our data frame. This is going to be really useful. We can now compute the average error for both candidates. Was there a systematic direction to how wrong the polls were? In this case, let's compute the average error across candidates. We're going to group by candidate, compute the mean error as the average of the errors. And we'll see that Clinton had a minus 0.38 error on average in the polls, where Trump had a minus 4.6 error on average in the polls. What does this tell us? Can anyone draw any conclusions from this table? You speak a little louder, I'm sorry. Yeah, the prediction on Clinton, the polls were correct on Clinton generally, right? The average error was close to 0. That's exactly what we want to see most of the time. We want to see as many guesses that are too high as there are guesses that are too low, right? We want to see symmetry around the truth, generally speaking. We want to see that's an unbiased estimator when we have as many guesses that are too low as there are guesses that are too high. And if the average of our error is 0, then we actually have done a pretty good job. We can ask questions about how wide our errors are as well, but we generally want to see errors with a mean of 0. This mean of negative 4.6 tells us that our polls were systematically underguessing how many votes Trump was going to get. There was a negative bias in the polls. They were under predicting his actual election day performance. And this is why, I don't know how many of you still have trauma memories of the 2016 election, but all of the Washington Post and other models were 99% Trump's going to lose, 99%, no chance that he's going to win, no chance. But the polls were wrong, right? The polls were systematically wrong. Here's what those errors look like as a distribution. And this is also, when I talked about symmetry, we can kind of see it here. For Clinton, the distribution of the errors across the polls, that is, when we take those errors and we make them a histogram for each candidate, we can talk about them as a distribution, right? We can look at how they're laid out as frequency on the X and the value of the error on, frequency on the Y, the value of the error on the X. And we can see that for Clinton, the distribution is roughly symmetric around 0, right? 0 is this dotted line. And we can see that we had about as much mass to the right of 0 as we do to the left, a little bit more to the left. And that's why we have that negative 0.3, right? Slightly more to the left. So there's a slight negative bias, but it's small, right? We have a lot of mass above 0. And that's precisely what we want to see in our errors to show that our prediction is unbiased. In the case of Trump, we can see most of the mass of the distribution is underneath 0, right? There's only a little bit of mass above 0, right? If we were to sum up the number of cases that this area represents and sum up the number of cases that this area represents, we have dramatically more cases under 0 than we have over 0, meaning way more polls under-predicted his performance than over-predicted his performance. So this is a quick way to visualize error distributions. Turns out a ton of what we do in statistics is thinking about error distributions. We're going to spend a ton of time talking about the distributions of our errors, both this semester and then next semester as well, if you continue on to learn about generalized linear models next semester. Now, sometimes we might not be interested in the direction of error. We might be interested in the magnitude of error, right? Rather than thinking about, is it positive or negatively biased, we might want to know how much variance is there around the truth, right? How noisy are my polls? So like if I have the truth is 50 and I have one poll that guesses 90 and another that guesses 10, the average of those two errors is 0, right? But that doesn't tell me how bad my guesses were. It just tells me that on average they zeroed out if I take their mean. What root mean square error does instead is it effectively computes an absolute error by taking, again, our y hat minus y, and in statistical notation, a hat, which is that little triangle, predicted y, right? So if we put a hat on something, that means that's our guess from whatever exercise we're going through. In this case, it's a poll, but it could be a statistical model that gives us a prediction. Could be a lot of places we get it from. So we're going to just take our simple error and we're going to square it. And what does squaring that error do? So let's say we have here minus 5.2. That has a direction. What's going to happen when I take 5.2 minus 5.2 squared? It'll become positive. It'll be 25 something, right? I don't want to square 5.2. Okay, so we can then compute that, compute the average error magnitude, so we can divide it by n. In this case, let's pretend it's 1 because we're only looking at one observation. Well, we want to look at how big is the error on average across the full data set, and then take the square root of that, right? And the square root of that will compress it back onto the scale of the original data rather than on a squared scale, because it wasn't wrong by 25, it was wrong by 5. So if we do this exercise, negative 5.2, 25 over 1, square root of that, we're back to 5, right? But we flipped the sign on the negative. This way, negative and positive, guesses that are too high and guesses that are too low do not cancel each other out anymore, right? When we add these all up, they do not cancel each other out anymore. So we're going to sum up all the errors. We're going to divide by the number of observations that we summed over, and then we're going to take the square root of that. So the root mean square error will, unless there's a strict positive bias to the errors, the root mean square error will always be greater than, it will always be greater than or equal to the absolute, to the prediction error, right? Or the average prediction error. So in this case, what do we see? This is just how wrong were they ignoring direction, ignoring the direction of the error. We can see that Clinton had a root mean square error of 8.2, and Trump had a root mean square error also of 8.3, right? So let's look at these distributions again. What can we say about the spread of these distributions? Ignore their location, right? The location is where they centered on the x-axis. Let's look at the shape of them. They look very similar to me, right? If I were to center this distribution here, the shape looks very similar. So the absolute error across candidates was similar, right? The spread of the errors was similar, but there was a direction to the errors on the polls for Trump, right? There was a bias. So the magnitude of the error was similar, but there was a direction to it. In the case of Trump, there was a bias to it. So the spread of guesses was similar across both candidates, right? The variance, that is, how different was each guess from each other guess, was similar. How different was each guess from the average? That was similar. But Trump's was simply shifted a few points further down than it should have been, right? That's typically what we would think of as the intercept, right? The intercept was too low. So conclusions on errors. Polls had similar magnitude of error for both candidates, root mean square error. That means the sampling technology, right? The basic premise of like inferring something from this population was correct. The problem probably was the population of people who responded to the polls was not the population of people who voted, or the population of people who voted were systematically lying or did not finalize their vote decision until the last minute. And we might have a social desirability bias in the polls. So we have two potential sources of bias there. Either we're using the incorrect population or there's a social desirability bias. The truth is it's probably a mixture of both of those things. Poll errors were consistently negative for Trump, were 0 on average for Clinton. That's why we have underprediction for Trump, right? This is something that has received an incredible amount of attention in the polling industry. If you want to go back and read Nate Silver's commentary on this following the 2016 election, I do not recommend you do that, but there was plenty of ink spilled, plenty of writing on this phenomenon. Okay, so how many polls called it right? So one way we can think about quantifying error is through absolute error, root mean square error, or through the average error, right? Just the mean error. So we can think about the direction and the magnitude of error. Was the direction negative or positive? And how wrong was it on average, right? Those are two different questions we can ask. How much absolute error was there, and was there a direction to it? Another way we can think about error is through a classification approach. Ultimately, the outcome here is binary, right? Who's going to win the election in this state? Trump or Clinton? Who's going to get more votes, right? That's a binary outcome. Did Clinton win? True or false, right? So we can ask, instead of what the error was, we can ask how many polls called it right. We can ask for classification outcomes, right? This is a kind of different approach to thinking about this. And this is obviously something we might see quite often in the case of political elections, but it's also something we see in medical applications for diagnostic tests, other kinds of things like that, right? So what we can do is we can make an average prediction for each state across all of the polls we had for that state. That is, we can pool, we can kind of borrow information across different polls, take the average, right? That should smooth out some of those errors. Whichever candidate has the highest average polling number, we will say the polls predict that candidate to be the winner, right? So we're going to take the averages across all the polls, and then whoever had the highest average across all the polls, we'll call that person the winner, and then we can compare that to the truth. The way we can do that is we can create a new data frame called poll winner, where we take our polls results, that's the joined data frame where we have the polls and the results attached to it. We're going to group it by state and candidate, and then we're going to compute the average value for the poll results across all of the polls for that state. And then we're going to use filter, we still have grouping on, to take the maximum value of poll mean for each state. And what that's going to do, it's a little bit of a like a clever workaround, but what's going on? Okay. Yeah. Okay. I'll show you. Sorry, exactly what that does. That first, let's look at this. So here, we've computed the average for each state of the polls for Clinton and Trump, right? So in Alaska, the polls on average predicted a 35.8% vote share for Clinton and a 46.3% vote share for Trump. But this alone doesn't tell us who won, right? If we use this filter condition with a state grouping on, what it'll do is it'll take within each state, return only the highest value for poll mean. So within Alaska, we're grouped by state. Candidate is going to get undone after we do the summarize. It's going to peel off the last layer of grouping every time we run summarize. And it'll tell you that, right? R will tell you summarize has grouped output by state because it already grouped by candidate. So it's flattened by candidate already. You can't do any more grouping by candidate unless we ungroup state, right? So it's going to take the state grouping Alaska, Clinton, 35.8, Alaska, Trump, 46.3. Then it's going to return on a filter only the maximum value of poll mean for each state. And that's going to be the winner, right? According to our polls. So in Alaska, the maximum value between 35.8 and 46.3 is 46.3. So it's going to return Trump as the winner, right? And Alabama, 37.6, 56, it will return Trump as the winner. So in this data frame, right now, we have 100 rows. After I run that filter command, I will have 50 rows, right? Because I've removed the loser from the data frame. I've removed the candidate who received a lower poll score from the data frame. Now we have a list of predictions for who would win the election based on these polls, right? So this is saying that it's going to say Alaska, Alabama, Arizona, Trump, Trump, Trump. And then Arkansas, 2, California, Colorado, Clinton, Clinton, right? So it's going to turn those polls into an actual projection. Now we can look at how many states the models predict each candidate is going to win. 26 for Clinton, 24 for Trump. But of course, that's not how we decide elections for president. We use the Electoral College to do that, right? So we need to turn this into a projection of electoral votes, not just numbers of states that were won. It's an arcane and ridiculous system, but it's what we do. So we're going to go back. We're going to take poll winner, right? And let's look at that data. There's maybe a more efficient way I could have coded this, but it doesn't matter. Now we want to go back and we want to get the electoral votes for each state. And remember, I had that in polls. So in polls, what I want to do is I want to select out state and electoral votes. But remember, we have duplicated states within that polls data because we could have multiple polls within a state, but electoral votes are constant within a state. So if I take only these two columns, I'm going to have a lot of redundancy, right? Because I've kind of removed the thing that varies. I've removed the poll result. But here, so for Texas, I have 2 rows with 38, right? I don't need that. So I'm going to use the distinct function to remove duplicates. The distinct function will remove all entries that are not unique across the columns that are present in the data. So in this case, this column is unique up to this point, but now it's going to see this one, that is non-unique, right? So this column is going to go. This column is unique, this row is unique, this row is non-unique, it's going to go. So we're going to remove all non-unique columns from the data. We're going to go from we're going to go from what we had there down to, now you can see we've removed that second row that had Texas, that second row for Wisconsin. And now we have a simple 50-row data frame that has the state code and the number of electoral votes for that state. And we're going to use our join tool again to attach that to our poll data. So we've called the winner. Let's now attach it to our predictions based on the polls. Our predictions were that Trump would win Alaska. And if that's true, he gets 3 electoral votes. Our prediction was that Clinton would win California. If that's true, she gets 55 electoral votes. We don't need to count the states. We need to count the electoral votes, right? So we use a join to reattach that data back onto our projection. Now I'm going to group by candidate, and I'm going to compute what share of the electoral vote each candidate was predicted to get by summing within each candidate the number of electoral votes they were predicted to get. And I'm going to convert it into a percentage. There's 538 possible electoral votes. So that's the maximum. So we'll divide by 538 total votes and then multiply by 100 to get it into a percentage format. So we're going to convert this into a percentage of electoral votes based on the polls. And we get a projection that says Clinton should get 63% of the electoral college vote, and Trump should get 37% of it. That's what the polls say, even though they have Clinton only getting 26 states and Trump getting 24. They're saying that the margin for Clinton's victory will be quite large, right? That's what the polls are saying. So we're going to turn this into a classification prediction, because before, what we looked at when we looked at errors in vote share, that's interesting on a national level, but that doesn't tell us who's going to win, right? That doesn't give us a prediction about who's going to win. This does. The actual result for Clinton was 42.2 in terms of percentage of electoral votes. On election, after the election was called, she was granted 227 electoral votes out of 538. So the error there, right, in terms of the electoral college projection, was pretty dramatic. A 20.6 point error, right? So in terms of the outcome of interest, that is who's going to win the election, the polls were incredibly wrong, right? It didn't look too bad when we said the error was -4, and that was a small bias, but in the outcome of interest, that is who's going to win each state and get those electoral votes, it turned out to matter quite a lot. Okay, so let's kind of take this from a practical example to kind of talking theory for a second. We can think about these are as potential outcomes, right? And we can kind of go back when we're thinking about causal inference, we had the counterfactual and the observed, right? Here, we're going to kind of use that potential outcomes framework again to think about classification error. So if we have a positive observation, we can have two categories for our observation. Let's call it a binary variable, positive or negative. That is, the result could be true or false. Our prediction could also take on the values of true or false. When we predict true and we observe true, we have a true positive. Our classification has resulted in a true positive. That is, we said something was going to be true and it was in fact true. If we predict something will be true and we have a false observation, a negative observation, we call that a false positive. We said it was going to happen, but it didn't, right? We had a false positive on that. Or I tested you for some disease, the test came back positive, you went back and got a more sensitive test and it came back negative. That's a false positive, if in truth you do not have the disease. If we make a prediction that something will not happen and it does in fact happen, that's a false negative. If we make a prediction that something will not happen and it does not happen, that's a true negative. So typically, we're looking for this diagonal to be what our tests do, right? We want true positives and true negatives. Typically speaking, we want to minimize false negatives and false positives. In practice, it's impossible to do that fully, right? There's always going to be error in any instrument or method we use to predict something, right? There's always error, even in the most precise of scientific instruments, right? But we can think about which kind of error we're willing to trade off on, right? In a diagnostic environment like medicine, you might be more willing to tolerate false positives than false negatives. Can anyone think about why that might be? Let's say I have a screening for cancer. Why might I tolerate a false positive more than a false negative? Right. If I get this false negative, I'm like, okay, cool. I don't have cancer. Done. I do not pursue further treatment. If I get a false positive, they're like, okay, we got a positive. We're pretty sure that's right, but it might not be. Let's get another test, right? Let's get a more sensitive test that's maybe more expensive or more invasive, right? Let's do a biopsy, something that has a lot more certainty, right? And then we can rule this false positive out with additional testing. But if we stop here at the false negative, we may miss a case and that might result in a death, right? So in the case of medical testing, we typically prefer false positives to false negatives. And we can design our tests to triangulate which direction they're going to go in terms of the kind of classification error they'll make. Sometimes we might prefer false negatives, right? We won't always prefer false positives. It depends on a lot of calculations, right? We might think of like it depends on the cost of missing a case, right? So like if it's about, for example, closing a school because of icy roads, and do I make that decision based on the weather forecast early in the night? Well, the cost of me missing it at that point might be kind of low, right? Who cares if I wait till the morning to make the decision about whether to close school because the roads are icy? I can wait, right? So I can go ahead and say, you know what, we're not going to close right now. We're going to wait, we're going to wait, we're going to wait, right? It really depends on the case. And this is kind of a place where something like a cost benefit analysis really comes into play. We need to think about what is the potential harm of misclassifying negative or misclassifying positive, right? We have to weigh the potential harms of misclassification, and they differ based on which side of it we're on. But this is the basic framework for thinking about classification error. We can have true positives and true negatives, false positives, false negatives. Sometimes you'll see these called type 1 and type 2 errors. I will not use that terminology because it's incredibly confusing. I would prefer to just say it's a false negative, it's a false positive, rather than calling it a type 1 or type 2, because I don't know what those mean, right? But we can talk about it in terms of, if that didn't make any sense to you, good. We'll stick with it because it doesn't make any sense. It's a weird old technique. But let's check our performance, right? So we know that the polls got it wrong. We know that there was, in fact, pretty substantial classification error in the polls. But let's compute it for each candidate, right? So let's take poll winner. We'll select state and candidate, right? So we already have this as only the winners are in this data frame. We're going to rename poll winner as candidate. So we're going to have a two-column data frame. It's going to have the state and the winner. We're going to take the election winner as a second, as coming from our results. We're going to compute in a similar way max candidate votes for each candidate to return only the winner. We're going to rename election winner candidate. And we're going to take state and election winner. So it might be hard to visualize what this is producing without actually seeing it. So let's see it. Here's what poll winner will return. So we have a two-column. Maybe we'll just do that. Okay, so we'll have the state and who won in the polls. And then this will return us a very similar data frame that has the state and who won in the elections. Right? State election winner. So we have two data frames, one with state poll winner, one with state election winner. What should I do now? Join them by state, right? So I'll use a left join, poll winner onto election winner, but the direction doesn't matter here because they're both 50 rows. Now we can look at poll performance. So we can see where we have matches. Poll said Trump would win Alaska, Trump won Alaska. Poll said Clinton would win Colorado, Clinton won Colorado. Right? So for these, we have correct classification for all of these. Right? And that's great. But let's turn it into a binary outcome. Does the poll winner match the election winner? We're going to do that with a mutate, and we're going to create a new variable called poll correct. Was the poll correct? And we can see here that now we get an additional column on here. It's going to be true when the two match. It's going to be false when they don't. Right? So this will flag those misclassifications, those places where the polls did not call the election outcome correctly. So now what we could do is we can compute the average performance of the polls. How often, on average, did the polls call it right? And by this metric, it actually wasn't that bad. They called 88% of the cases correct, right? They had correct classification for 88% of the cases. Now, in this case, our binary outcome isn't true, false. It's Trump, Clinton, but we can call Clinton true and Trump false, right? And so we can say here we can think about our error in the case of like Florida, right? If we say that Clinton is true and Trump is false, what kind of outcome would that be? That'd be a false positive. It predicted Clinton but the outcome was Trump. So if Clinton is equal to 1 and Trump is equal to 0, and I think I'm fine with that, then we have a false positive in this case, right? We called it for Clinton, but that didn't happen. So we have an 88% classification accuracy on the polls, which honestly, for most applications, I'm good with that. 88% classification is pretty darn good. But in this case, it was catastrophically bad because the Electoral College is a really swingy system, right? Because it's an all or nothing system and 50 different states. And some of those states were actually quite difficult to predict, right? A very small subset of the states were very difficult to predict. The overwhelming majority of states are incredibly easy to predict. Predicting California will go for the Democratic candidate before you even know who that Democratic candidate is going to be, you're going to be right 99% of the time, right? Predicting Vermont will go for the Democratic candidate before knowing who the Democratic candidate is, you're going to be right 99% of the time. Predicting the Republican is going to win in Alabama, you're going to be right 99% of the time, right? There's no uncertainty in a lot of these states. But in some of those states, there's an incredible level of uncertainty. And that's where all the difference gets made here. So let's get our misclassifications. We can filter for only those places where the poll was incorrect. Right, so I'm going to filter not poll correct. I could make this not poll correct equals true, but that's implicit when I have a logical vector, right? So because poll correct is already true, false, saying not poll correct will return only falses. So here I get the 6 states that were misclassified, right? We get Florida, Michigan, North Carolina, Ohio, Pennsylvania, Wisconsin. So that's 2 ways to think about prediction error. We can think about it in terms of a numeric error on a continuous variable, right? We can think about the magnitude of error, or we could think about classification as a binary outcome and think about classification error, right? So we can think about it in multiple ways. We can think about it for continuous variables in terms of the distribution of errors, and then we can think about the direction and magnitude of error. And when we're thinking about binary or categorical outcomes, we can talk about classification error, that is accuracy in terms of predicting the category that something belongs to. Let's take 5 here, and then we're going to get back. We're going to come back and we're going to get to linear regression, which is probably the most important topic we're going to cover in class and what we're going to spend just about the rest of the semester on. So yeah, take 5. We'll start again at 11. So linear regression, again, we're going to be spending the majority of our time together talking about how to work with linear regression. Linear regression is the foundation for just about all contemporary statistics. And that's both a good thing and a bad thing. But we'll kind of curtail talking about why that's bad until we fully understand why it's good, right? But it's effectively a model for thinking about relationships between variables being described by a simple line relating changes in one variable to changes in another variable. It's very similar to the correlation plots we've looked at so far, but it's going to extend it by adding not only a slope to the relationship, but an intercept to the relationship. And we're going to estimate those from the observed data. So first, let's talk about the basics. We're going to use the IPV data again, and you're going to use this for homework this week as well. The homework this week is easy. I know that this week's homework was hard, and I appreciate you all struggling through it, but I promise you this week's homework, if you understand how to use the LN function, should take you maybe 20 minutes. But I just want you to practice doing it a little bit. Right. I make y'all struggle through it sometimes because that's the reality of doing data work, is struggling through how to make something work. But and that I think there's some interesting subtle trickiness to the homework for this week in terms of how to interpret it. But sometimes I'll make it easy. This one's easy. But if you want to follow along, you can read the data back in from GitHub. You don't have to right now if you just want to watch. But that's a refresher on what the data looks like. Again, it's a survey at the country level and year level. So we have country, year level data. And we're going to ask a simple research question, right? This is kind of different than what we've done before. Now we're going to start formulating hypotheses and using our data to test theories, right? So our research question here, and when we say research question in this context, we're typically talking about a concrete question that can be answered using empirical data, right? It's generally not like a big topic. It's generally so in this case, we're asking, are secondary school completion rates for women associated with lower levels of acceptance of intimate partner violence? A bigger topic question would be, does increasing levels of education change attitudes on household violence or intimate partner violence generally, right? That's a big question. A research question is narrow, right? It's asking a very specific question of the data. What do we see in the relationship between school completion rates and levels of tolerance for intimate partner violence? And we're going to formulate this in terms of a theoretical hypothesis. That is, I'm going to spell out why I think this should go in a particular direction. So feminist theory suggests a negative association between schooling and tolerance for intimate partner violence, right? And the way this works, according to one interpretation of the theory, is that in places where women have more social and economic power, tolerance for intimate partner violence should be lower, because violence in the household, according to feminist theory, is a function of asymmetries in power between men and women in broader society, right? So if women have access to more power and more resources, which schooling provides in theory, right, then we should see lower levels of toleration for intimate partner violence, according to a pretty simple reading of feminist theory. Of course, it's more complicated than this. That's one way we could frame our expectations for what we would see. And as you're starting to write, as you're starting to become active quantitative researchers, I want you to start thinking about not just telling me what's going on in the data, but connecting it to theory, connecting it to what you already know and what you expect to see in the data, right? We all come to research from a particular background, whether that's from our own life experiences or from the research we've done, right? We've read a lot about our subject areas of interest, and we know a lot already. We have expectations about what we should see that are grounded in what we've seen before, grounded in prior studies we've seen, grounded in theories, right? So spell that out in your research. This theory suggests to me that this should happen in the data. And what we're doing is we're setting up implicitly a test of that theory, right? We're saying feminist theory suggests this should happen. Does it happen here? Yes or no? And we're engaging in a very time-honored practice of falsification, right? What we're doing is we're going to look for evidence that this is not true, right? We're going to engage in a practice of falsification because we're saying this is what the theory expects to happen. If we see something different, it suggests something different may be going on. If we see what the theory predicts to happen, then it's confirmatory. But typically in the sciences, we're looking for falsifiable statements. We're looking for a prediction of what we expect to see that could come out against the theory, right? There's a lot of theories that we could discuss that are not falsifiable, right? That there's no evidence we could ever bring to bear that could disprove the theory, right? Does a higher power exist? Does a God exist? We can never disprove that with empirical evidence, right? Does a lot of the evolutionary psychology gets accused of this often, right? That will take primates started to reduce their tails probably because of X, Y, and Z, and they're using the theory to extrapolate it. But we don't have a time machine that we could go back and actually see if that's what happened, right? All we can do is speculate. If we can't muster empirical evidence to come out in contradiction to the predictions of the theory, then that theory is called non-falsifiable, right? We're not going to get too much into the philosophy of science stuff. There's other ways to think about evidence, but the most traditional way in the science is to think about learning something and accumulating information, accumulating scientific knowledge is by testing falsifiable theories. We design falsifiable theories and we use empirical evidence to see if they hold up. And if it continues to hold up and hold up and hold up, hey, that's a pretty strong theory, right? The theory of evolution is typically not falsified, right? It's falsifiable, right? A species will adapt to the environment in which they're in, and they'll selectively mutate to better thrive in that environment, right? And we've seen, of course, we've seen evidence in support of it, but we also rarely see species that would not, that would exist if that model were not true, right? We rarely see contraindicating evidence for that theory, right? And we could kind of proceed through. There's like a whole epistemology of science we could do on this, but like, we want to make a statement that could be proven false. That's what a social scientific hypothesis, a good one, will do. It can be proven false with some hypothetical data. In this case, we suggest we're making an implicit prediction here that places where women have more social and economic power should have lower tolerance for intimate partner violence. So here, what are we predicting in terms of this association? We're saying, are they associated with each other? But here, we're actually predicting a negative association, right? We're saying that as secondary school completion goes up, tolerance for violence should decrease because of this theory. So this theory is telling us, this theory predicts that as schooling goes up, tolerance for violence goes down. And that prediction could be wrong, right? That's falsifiable. Not saying it's going to be proven wrong, but it could be in theory. Here is the observed data. We're going to do a scatter plot when we have two continuous variables. That's the easiest way to eyeball the relationship. So looking at this, roughly, we can kind of visualize that there's probably a negative relationship here. We tend to see that when secondary schooling is lower, the tolerance measure is higher. When secondary schooling is higher, the tolerance measure tends to be lower, right? And we can add our line to this. This is just the best fit regression line. We'll talk about how to compute this in a little bit, but we can indeed see that there's a negative slope here, right? So there does appear to be a pattern that for lower values in secondary school, we see higher values of tolerance for violence. For higher values in secondary school, we see lower tolerance for violence. The correlation coefficient here is a negative 0.38. So remember, correlation coefficients can range between -1 and 1, right? And so negative 3.8 is a relatively, it's a moderate negative relationship. Now, why do I always scatter plot things instead of just looking at correlation coefficients? Here are 4 pairs of variables, right? We have y1, y2, y3, y4 against 4 different x's. And for each pair, we have a correlation of 0.8 for these 5, or I guess it's 10 points. This is called the Anscombe quartet. But what do we see here? This is what we typically expect a scatter plot to look like. And this is the relationship we imagine most of the time. This is a simple linear relationship. This is a correlation of 0.8. This is also a correlation of 0.8. This is also a correlation of 0.8. And this is also a correlation of 0.8. Let's talk through these, right? This is the linear relationship. Here, we've got a nonlinear relationship. Pretty evident, right? That's a curve. A line does not describe that relationship particularly well, but for these 10 points, the correlation is 0.8, right? Here, we have a really clear linear relationship here, but because the correlation works as a function of a mean, it's pulled up by the outlier. And so the line gets shifted up because of this outlier, right? But we still have a correlation of 0.8. Here, we actually have a binary variable. It only takes on 2 values, here and here, right? But because it's a function of means, the average of this value and these values gives us a correlation of 0.8. Right? So I can't understate the importance of plotting your data as we start to think about underlying relationships. We don't know if we just compute a correlation, we don't know which of these relationships is actually present in our data. We have no idea, right? But if we look at it, we can see what's going on. Single, simple statistics can mislead you about what's going on in the data. Visualization is the best remedy to that. Strongly recommend that you always visualize your data. Always, always, always. Even if it doesn't end up in the paper you're writing or whatever you're working on. For your own purposes, just to understand what's going on, always visualize. Here's another example of a limit of a linear relationship. We have a really clear, I actually put like a 0.8 correlation between the two variables here, but I made it a function of a quadratic, made it a function of a squared relationship between the two. And what do we see? We see a really clear pattern here, but the linear relationship misses it entirely. It estimates a 0 correlation, despite the fact that y is clearly a function of x, right? But we've specified the incorrect functional form. Correlation is the wrong measure to use for this, right? So always look at your data, right? Correlation coefficients range between -1 and 1. We've already talked about that. Okay, so let's talk about lines. We can define a line, and this is just some geometry review real quick, as y equals mx plus b, where m is the slope, b is the y-intercept. So what does the slope represent? What does the slope tell us? It tells us the steepness of the line, right? How steep is the line? In mathematical terms, it tells us how much does y change for a unit change in x. If x changes by 1, how much does y change? So if x increases by 1, y increases by m. What does b tell us? Tells us the location of that line, right? So m tells us the direction of the slope, but b tells us where it sits on the y-axis when x is equal to 0, right? When x is equal to 0, 0 times m is 0. So then we start at b. So when x is 0, what is y equal to? That's called the y-intercept, and it's where the line crosses the vertical axis. So what does the line y equals x plus 2 look like? It's often easiest to start from the intercept. So what's the first point I should, if I'm going to start at the intercept, what's the first point I should put up here? When x equals 0, what is y? Y equals 2. So here's x equals 0. Let's call this y equals 2. So the intercept is there. Now, what's our slope for y equals x plus 2? Our slope is 1. So let's draw another point. What happens when x is equal to 1, y is equal to 3? And if we have 2 points, we can actually draw our line from there, right? We can extend this easily to -1 as well. When x is equal to -1, y is equal to 1. Pretend that's straight, right? And then we can extend this out to infinity, right? That's our line. So we've established the intercept and the slope, right? So y equals 1 times x plus 2 will give us that line, right? That's what it looks like if we plot it. Y equals 2x plus 2. Right now we've doubled the slope. The slope is 2. So you can see that the steepness of the line increases, right? The slope is rising faster. That is, so when x goes up by 1, y goes up by 2, meaning we get a lot of vertical motion in it. minus 2x plus 2 flips the direction of the slope, right? So when the slope is negative, we get a decrease in y for an increase in x. 0.2x plus 2 means that for every 1 unit increase in x, y only goes up by 0.2. So for y to go up by 1, x has to increase by 5, right? We can see that we start here at 2, and to go to 3, we have to go up on x by 5 to get a 1 unit increase in y. Right, so we could compare that here to there, right? The slope is 1/5 as steep here. X plus 0, right? Just intersects the y-axis at 0, right? It goes through the origin 0, 0. X plus 2 just shifts the intercept over, shifts the intercept up by 2. So the line just moves, gets bumped up. Okay, x minus 3, line bumps down, right? So that's intercepts and slopes. Slope changes the steepness or direction of the line. Intercept changes the location of the line. Okay, so we can describe the relationship between a predictor variable x and an outcome variable y. We're going to take that same basic tool of the line and now put it in terms of variables, right? So y equals mx plus b. M is the slope, or the increase in y for a 1 unit increase in x. And b is the expected value of y when x is equal to 0. It's the location of y when x is 0. So we can take this basic format, y equals mx plus b, and we're going to rewrite it in a statistical notation now. So this is what we would see in a geometry class. For linear regression, even though this looks quite different, it's actually the same thing. Instead of y, we're going to say the expected value of y, our prediction for y, the expectation of y equals beta 0. This is beta, capital, it's a Greek character beta, beta 0 plus beta 1 times x. Here, m is being substituted for beta 0. I'm sorry, b is being substituted for beta 0, and m is being substituted for beta 1. Beta 0 is our intercept. Beta 1 is our slope. E of y stands for the expected value of y. In statistics, when we see a capital E surrounding something, that means the expected value of. So the expected value of y is equal to beta 0 plus beta 1x. Now, to turn this into an actual prediction for y, rather than the expected value of y, because we always have error relative from a prediction to an observation. So if we want to retrieve this and express it in terms of the observed values of y, we can write the equation as y equals beta 0 intercept plus beta 1 slope times x predictor plus epsilon. Epsilon is what's called an error term. That error term represents how far away from the observed value is our prediction, right? So if we add, remember our prediction for y is beta 0 plus beta 1. But of course, the observed value for y could be different from our prediction, right? So we're going to add in this epsilon term to allow the actual observed values of y to differ from the true regression line, to differ from the predicted regression line. This sounds a little wonky, but I'll show you how this works in a visual in just a second. So epsilon here is the error between the fitted line and the actual observed coordinates xy, or the observed data, right? The difference between the observed and the prediction. The regression line gives us the prediction. Beta 0 plus beta 1x gives us the prediction. When we add epsilon, we get to the observation. Okay. So epsilon is in effect the distance between the line beta 0 plus beta 1x and the actual observed values of y. And y equals beta 0 plus beta 1x gives us a prediction for the values of y based on the values of x. And we might rewrite this in terms of actual observations. You can see here that I've got capitals. When I have a capital, what I'm referring to typically in statistical notation, a capital Y refers to the vector Y. Capital X refers to the vector X. That is, a list of Y's is equal to some intercept plus beta 1, which is, those are both constants. Those are going to be numbers, not vectors, times the vector X plus a vector of errors, epsilon. But we can rewrite this, and again, this is a lot of notation stuff, but you're going to see it written this way, so I kind of want us to get comfortable with it. We can say that the individual observation, y sub I, right? We can compute this line, y sub I equals beta 0 plus beta 1 x sub I, to get a prediction for the value of y sub I, right? Technically, what we're getting here is y sub I hat, right? We're getting the prediction for y sub yi, and the actual value yi will be equal to beta 0 plus beta 1 xi plus epsilon I. We have an individual error term for every single observation in the data in terms of how much it differs from the regression line. So if we want to retrieve an individual observation, we can add the intercept plus beta 1 times its value for x for that row plus the error term for that row. So this is written in terms of a single row of the data. Here, this is written in terms of vectors, right? So the capital notation gives us vectors, the lowercase notation with a subscript gives us individual observations. So for observation I, the expected value of y sub I is beta 0 plus beta 1 times xi. So beta 0 equals 2 and beta 1 equals 1.5. What's the expected value of y when x equals 4? Take a second and see if you can compute that. You have everything you need in this equation and with these givens. Just solve for y. Let's write it out. Y sub I equals, what's beta 0? 2. What's beta 1? 1.5. And what's x?
4.
That's it. That's our prediction for y. Right? So we get what? 2 plus 6. So we get 8. Y sub I, our prediction for y sub I, if beta 0 is 2 and beta 1 is 1.5 and x is 4, we predict that y will be 8. Or we expect that y will be 8. Our expected value for y is 8. Another way, and this is kind of skipping ahead a little bit, but the expected value is equal to the mean. Our average prediction will be 8. Of course, we're going to have some random noise around that we'll talk about later. Okay, so let's try it when x equals 2. What is y equal to if beta 0 is 2, beta 1 is 1.5, and x is 2? 6. Right? So in this case, we'll do y sub I equals 2 plus 1.5 times 2. That's equal to 6. No, it's not. Sorry. 1.5 times 2 is 3, plus 2, 5, right? So if x is 2, then y sub I, our expected value for y sub I is 5. Okay, here's just a slide on the hat notation, right? Y hat is the expected value of y, not the observed value of y. With our polls, right? The poll could be called election hat. It's our prediction for the election, but the actual election result would be just called election. So if we wanted to just use a single variable name, we could distinguish between the two with a hat, right? This little triangular caret on top. So y hat equals beta 0 plus beta 1x. Epsilon is equal to y, and I'm just putting observed here to distinguish the two, but we don't need it. Epsilon is equal to y minus y hat. The observed minus the predicted. Actually, I think it's the other way around. I think it's y hat minus y, but we're usually going to square, and we're going to take the root mean square error every single time we use these. So the direction doesn't matter ultimately. But epsilon is the difference between the prediction and the observation. So let's understand the regression line for real data. Here are two sets of x's and y's, a vector x, a vector y. Let's say beta 0 equals 0.05, beta 1 equals 0.95. And let's try and compute y hat. We actually don't need y to do this at all, right? Y's are observed. We can compute the errors in a second with it. But let's estimate y hat for row 1. Beta 0 is what? Okay, 0.05. Beta 1, 0.95. X1 is equal to, what's the x in row 1? 0.53. So let's do the math. What is y hat for 1? 0.05 plus 0.95 times 0.53, whatever that is. Y hat 2 equals 0.05 plus, what's x2? We'll call it negative 0.4 times 0.5. Oh, right. Oops, did that wrong. Beta 1 is 0.95.
Yes.
Times minus 0.4. Okay. So we could compute, if we have our regression equation, beta 0 plus beta 1x, and we have values for beta 0 and beta 1, we could compute a third column here called y hat. That is the predicted value of y given this regression equation. Okay. Once we've done that, we can compute epsilon, right? So in this case, let's say
The first one is 0.55.
it's what?
0.55.
Okay. Equals 0.55. What about the second one? It's going to be pretty close to negative 0.35. We'll just call it that.
Yeah.
Right. Okay. So let's estimate epsilon for these. Right. We know that y1 is equal to 0.528. No, that's x. 0.481. And y2 is what? Minus 0.5. So, well, we'll just call it 0.5 and round to make our life a little simpler. So we can then compute epsilon 1 is equal to, so y minus y hat, we'll do it that way, equal to y1 minus y hat 1. Something like that. That guess was just about right. Now for y2. Y2 minus y hat 2. We have y2 is equal to negative 0.5. Y hat 2 is minus 0.35. So we get minus 0.5 minus plus 0.35. The negatives will cancel. And so we get an error there of about negative 0.15. Right? So that's how we can kind of use the regression line to compute expected values and then compute errors from those expected values. Typically, we're going to automate all this. We're very rarely going to do it by hand, but we can, right? And sometimes we will do it by hand if we just want to know, okay, I have my regression equation for the effect of years of education on wages. What happens if someone has a college degree versus a high school degree, right? And we'll kind of get through that as we talk more and more. So this is a plot of our data. This is the same data that we've got here as a scatter plot, right? And I've estimated a regression line. Beta 0 equals 0.05, beta 1 equals 0.95. Don't worry about how I estimated that line, but those numbers are right. There's the line. Intercept at 0, y is equal to 0.05. The slope of the line increases for every increase in x of 1. Y increases by 0.95 because our intercept was 0.05. When x equals 1, y equals 1. When x equals 2, y equals 1.95. Yeah. We can see, though, that for each point, we're close, but there's nowhere that we're exactly on the line. Right? Our line does not pass through any of the individual points. Sometimes it will, most of the time it won't. What it does is it computes a best fit line. Linear regression computes the line that minimizes the root mean square error. What it does is, remember, the root mean square error is how wrong is the guess in absolute magnitude from the prediction. Right? So if we were to take our epsilons, we were to sum them all up, square that, to compute the epsilons, square them, sum the squares, compute the average, and then take the square root, we're going to get what the linear regression method is going to do is it's going to provide us the line that provides the smallest amount of error possible. Right? It's going to minimize the absolute error. That is, it's going to find the line that minimizes, on average, the distance between the points in the line for all the points. So it will find the line that minimizes the absolute distance between the points and the fit line. We call that the best fit line. That's what the linear regression does. So it minimizes the root mean square error. Don't need to worry about how it does that yet, but that's what it does. So let's add y hat to this regression line. So here's our regression line, right? Just trust me that that's the regression line for now. That's the best fit line. These red dots are y hat. Linear regression always predicts the expected value of y will be exactly on the regression line. So y hat for every value of x will be on the line. Right? Our prediction for y falls exactly on the line. So y hat is always on the regression line. It's always on the best fit line. Epsilon is the distance between the observed and y hat. How far away is the observed value from the expected value? So these errors show us how far each point is from the actual regression line. So how do we do this? We use a technique called ordinary least squares. is the most common way for estimating regression. That is, we minimize the sum of squares. We minimize the root mean squared error. So this method seeks to minimize the distance between y hat and y across the vector, right? So we want to minimize these distances. But again, we're going to square them to ensure that they're always positive, because we don't want these negatives and positives to cancel each other out, right? We want to minimize the absolute distance, not the relative distance. So we minimize what's called the sum of squared residuals. That is, we sum the square of each of these residuals. So the residual here, I'm sorry, residual is another name for the regression error. A residual is the difference between the observation. It's another name for epsilon. We could call the vector epsilon, we could call that the residuals, right? And so what we're trying to do here, let's say this is like a -1. We can actually compute this, but we're going to square each of these residuals. Say, hey, this is -1 and this is 2. That'll be -1 squared is 1, 2 squared is 4. So it'll be 1 + 4, 5, right? This, but we can imagine all kinds of different regression lines here, right? So we could, in theory, draw a line that goes like this, right? We could, in theory, draw a line that goes like this. We could, in theory, draw a line that goes like this. And from each of those lines, we could compute errors. How far away is the observed from where the y hat would be if my line was different, right? So let's say my line was here, right? My y hat, let's put it here. My y hat for this point would be here, right? Now in this case, the error would be pretty dramatic. We'd have a much larger error here than here. And we'd also, at this point, have a much larger error. I don't know, maybe it'd be the same there. But what we'd be doing is averaging across the full vector to look at how much absolute error is there for different lines. And we're looking for the exact line that minimizes the total amount of error that we have in the system. Okay, sorry. Within the ordinary least squares context, we call that the sum of squared residuals, right? We're not actually going to calculate the average. We're just going to sum all those squared residuals. So that effectively is going to be sigma of epsilon squared, right? The sum of squared residuals is just that. If we add up all of the squared errors and we seek the line that produces the minimum value for this. Oh. Clearly thought about that. Okay. So we solve for the minimum value of yi minus beta 0 minus beta 1x squared. Right? We solve for the minimum value of this equation, the sum of squared errors or residuals. Error, residual, same thing. Sometimes you're going to see this expressed using matrix algebra. We can compute the regression equation using matrix algebra, and this is in fact how R does it. It's the easier way to do it by multiplying x transpose times x inverse times x transpose y. So we could actually, if we have the matrix x, if we have the vector x and the vector y, we could use matrix algebra to directly compute our vector of betas, or I'm sorry, our matrix of betas. Don't worry too much about it. Let the computer handle that part. But sometimes you'll see it expressed this way. So x transpose x inverse times x transpose y will give us our betas. We talked very briefly about matrix algebra at the beginning of the semester. You're never going to really need to use it in most applications, but it's the technology that's under the hood of a lot of the software we're going to use. Okay, so let's estimate a regression model in R. Turns out that looks hard, but it turns out this is just the math. What we do in R is actually incredibly simple. So let's create two vectors, y and x. Y is going to be 1, 2, 3, 4, 5. I'm sorry, x is 1, 2, 3, 4, 5. Y is 2, 5, 1, 8, 10. To compute a linear regression model in R, I use the function LM. Stands for linear model. And what I provide to LM is a vector of y's and a vector of predictors x's. Typically on a regression equation, we will call, you'll hear me, sorry, use this terminology a lot. When we're looking at a regression equation, y equals beta 0 plus beta 1x, I will call y my outcome and x my predictor. You may hear people call this the dependent variable and the independent variable, but we're honestly rarely using a kind of experimental framework where we, mess with an independent variable, or we, so where we have some kind of intervention. So I think it's better terminology to call this the outcome and the predictor, right? That's not implying a causal framework. We're saying if we know x as our predictor, we can kind of get a prediction for our outcome, y. Sometimes you'll hear that called the left and right-hand side of the equation as well. And the reason for that is that y is on the left and x is on the right. The outcome is on the left, the predictor is on the right. So y tilde x, right? That same symbol that we use for case when, we'll use here. This is R's formula notation, and it basically tells us that y is a function of x. So a linear model where y is a function of x. So I'm going to estimate this model using LM. And now in model demo in R, I will have an LM object. It will store the output of a linear regression model. There's a lot in that object, but for now, I just want to look at the coefficients. So I'll use coef to extract the coefficients from model demo. And I'll get two terms. I'll get an intercept and x. This is beta 0. This is beta 1. This is our coefficient for x, meaning the thing that we multiply x by, beta 1, right? So our beta 0 here is minus 0.5. Our x is 1.9. We can write this line as y hat I equals beta 0 plus beta 1 x. Our predicted value for y is equal to beta 0 plus beta 1 times xi. And in this case, we could write that as y hat I equals minus 0.5. What's beta 1? 1.9 times xi. That's our regression line. So we can go from these results on the console to a mathematical equation describing a linear relationship. Yeah? Cool. Could not be simpler. LN, that's all we got to do. Here's our observed data. That's what we just described x and y as. Here's our regression line. I'm adding, using the geom AB line. It's a geom and ggplot where I can provide it with an intercept and slope. So I'm telling it, here's the intercept. It's the first coefficient from model demo. Here's the slope. It's the second coefficient from model demo. It's going to plot that regression line for me. And we can see that it roughly passes through the middle of the points, right? This is the line that minimizes the squared error, the sum of squared error. It's the line that produces the least error possible for a linear relationship. Okay, so let's ask a question with regression. Are secondary school completion rates for women associated with lower levels of acceptance of intimate partner violence? What am I going to be looking at here? What, in a regression context, is this statement asking? What parameter am I really looking at in the model? What I'm looking at, beta 1. I'm asking, is beta 1 negative? Is the slope negative? That is what this question in mathematical terms is asking. For higher levels of secondary school completion rates, do I see lower levels of tolerance of intimate partner violence? So effectively, I'm asking, as X increases, does Y decrease? That's a negative slope. So I'm suggesting that there's a negative relationship between X and Y. And the way we'll look for that in a regression is by examining the value of beta 1. So the outcome here is, what's Y? Yeah, tolerance for violence. And what's X? Predictor? Secondary schooling. Exactly. So we're going to say, can I predict tolerance for intimate partner violence by knowing the value of secondary schooling? That's effectively what I'm asking. If I know secondary schooling, do I learn what tolerance for intimate partner violence is? And I'm predicting that should be a negative relationship between the two. So we can write this as the expected value of the acceptance of intimate partner violence for some country year I is equal to the intercept plus the slope times secondary school completion. In plain language, that's what I'm estimating. Our implied prediction is that the slope will be negative. So let's look at this. Here is the basic anatomy of an LN. Call an R. We already said it's Y by X, right? Y is a function of X, but here we're going to say Y is the variable beat goes out. X is the variable secondary school. And we need to tell it where those variables are coming from. So we're going to tell it the data that you should use is the data frame IPV. So if it's a data frame, we can just give it column names, right? So the first column you're going to use for your Y variable is beat goes out. The second column you're going to use for your outcome, for your predictor variable, the secondary school. Those both come from IPV. And then let's extract the coefficients with coef. So after we've estimated our model here, right, we've stored IPV model is now an object that has a lot of data from this linear regression model. And we're going to pull the coefficients out of it. I have an intercept of 40.18 and a slope of minus 0.47. What does that intercept indicate? What does that intercept tell us? When secondary schooling is 0, our regression model predicts that tolerance for intimate partner violence on this measure will be 40.2. So when women in a country on average have no exposure to secondary schooling, we expect the tolerance to be about 40.2. That's what the model tells us. For every 1% increase in exposure to secondary schooling, what happens? What do we expect to see? Tolerance goes down by 4.8, right? So for our model says that when women have no secondary schooling, we expect to see a tolerance at 40.2. But for every percentage point increase in secondary schooling, we expect to see tolerance decrease by negative 4.8. This is what our regression line says. We start at about 40, right? That's our intercept, 40.2. And then we can see for a 10-point increase in secondary school, we should see about how much of a decline for a 10-point increase? Negative 4.7, right? So we go from 40 to about 35 when secondary schooling increases by 10, right? And then down to about 31 when secondary schooling increases by 20, and on, right? So this is the regression line. And these are the black dots are the observed data. Right? And we can see that the regression line roughly passes through the middle of the cloud of points. That's what we hope to see when we look at a regression line. Of course, when we flash back to that Anscombe quartet, regression lines don't always pass through the middle, right? Here we have a linear relationship and it passes through the middle. This is a regression line. Does it pass through the middle of the points? Kinda. And I mean, it minimizes the error, but it's not really a great description of the functional form. Here, yeah, it minimizes the error, but it's not a very good description of the functional form. Similarly here, it minimizes the error, but it's not a great description of the functional form. So we always want to visualize it. Okay, so again, observed data, regression line. What are these? What would we call these in terms of our regression notation? The red dots are y hat, or our expected values of y. So if we know x, our regression line tells us that y hat should fall exactly on these lines, right? So for each value of x, we get a prediction that falls exactly on the line. And then those are our residuals, or our errors. Right, the dotted lines indicate the distance between the observed value and the predicted value. These are all the components of our regression model, right? We have our observed y's, our observed x's, our predicted y's, and our residuals, right? In addition to our coefficients, we have the entire model at that point. So how would I interpret this? Here's a sample paragraph for how I might write this up if this were a study I were conducting. I see a coefficient of 40.2 for intercept and a slope of negative 0.47. I might write, for example, on average, women in countries where women have higher levels of secondary education have lower levels of acceptance of domestic violence, right? So I'm giving a high level interpretation of the findings first. And I'm talking in terms of averages because remember, these are expected values, which is just what we think is going to happen most of the time. It's going to happen on average, but it may not happen in any single case, right? Because honestly, our guesses are like way off in a lot of places, but on average, they're right, right? If we look for the kind of average results across the data, they're correct. So on average, women in countries where women have high levels of secondary education, so start with a high level summary of what you found, and then go into a detailed summary of what we found. For example, the model predicts that y hat is equal to beta 0 equals 40.2% of women in a country in which 0% of women have a secondary education, approve of a husband beating a wife if she goes out without telling him. In a country where 20% of women have a secondary education, this model predicts that 30.7% will approve of intimate partner violence. There's a negative linear relationship between average levels of secondary schooling and women's attitudes about intimate partner violence across countries. So I'm starting with a high-level summary, ending with a high-level summary, giving my kind of supporting data on the intercept and slope and interpreting that for my reader in those paragraphs. You always want to interpret the numbers. Don't assume your reader knows what a beta is, right? Tell them what it means, right? So, and here, you know, that 1% difference might not be very meaningful, right? Increasing a country from like 10% secondary education to 11, that's not really a meaningful difference, but a 20% difference might be very meaningful. So I'm going to choose a meaningful difference to write up. So I'm going to basically ask here, what I'm doing is I'm assuming that xi is 20, right? And I'm going to compare this number to this number implicitly, right? So in a 0% education country, I have 40.2. In a 20% education country, I have 30.7, implying about a 10-point drop, right? Now we can decide whether that's meaningful or not, but that's ultimately what we get out of the regression equation. So we can turn this into this paragraph, right? And ultimately, that's a hard thing to do, but as you kind of work through developing your skills as a quantitative researcher, you're going to have to learn how to turn these two numbers into this whole paragraph. right? And that's where the writing comes in, right? We can do the math, but we also have to interpret it, right? The interpretation is absolutely key. Okay, so that's it for today. Next time, we're gonna get into multiple regression, where we talk about what do we do when we have multiple variables we want to use to predict y. And we're going to talk about different ways we can set up the relationship between y in a system of x's, maybe not just one x. We're going to keep pushing regression forward through the end of the semester. Again, regression is the single most important tool in contemporary applied statistics that you're going to see. And just about every other tool we use comes from linear regression. The homework for this week, again, is, I'm not done screen sharing yet, is pretty simple. It's posted now, but what I'm going to ask you to do is practice with regression. Use the data we use today, but we're going to switch out the outcomes. Instead of secondary school, we're going to use no media. And I want you to estimate a linear model using those two variables. I want you to compute the expected value for the outcome when the predictor equals 50, which you can do manually, but R also has a function called predict that if you want to experiment with, you can use. But you actually don't need to do it because you could just look at the numbers and do the math, by paper. Then do another computation for when the predictor is equal to 90. And then compare the findings and interpret their meaning, similar to the paragraph I just showed you. Yeah, pretty simple. This shouldn't take you too long, especially compared to last week's homework. But I want you to get a little bit of practice running these models. And if you want to toy around with different variables in the data or other data sets and running models, I encourage you to do that. Okay. Anything question-wise before